Hello everyone, my name is Fabian Perez and I'm going to present UnMix-NeRF, Spectral Unmixing meets neural Radiance Fields. This work is done by the Universidad Industrial de Santander and Caus University, with myself, Sara Rojas, Carlos Hinojosa, Hugo Rueda Chacon, and Bernard Gunner. NeRF represents a scene as a continuous field and renders novel's view by node volumetric integration along camera arrays. It enables high-fidelity novel view synthesis and reliable geometry estimation from multi-view images. Classic NeRF is RGB only. It reconstructs appearance and geometry from images, but it doesn't extend to other sensing modalities. As a result, it doesn't identify which materials are present in the scene, and segmentation typically requires modifying the pipeline or attaching an external pre-trained model. For example, one of the limitations is due to metamerism, since we only observe 3 channels. 2 different materials can match in color under one light. When the illumination changes, the match breaks and the difference becomes visible. And why material understanding matters? Look at the scene. A robot must choose between a plastic cup and a ceramic mug for the microwave. If it cannot tell which material is present, the action becomes unsafe. RGB captures color and shape, but not what things are made of. Spectral imaging samples many wavelengths, forming a cube of data. Each pixel has a spectral signature, and that's far more discriminative than RGB, helping apart materials that look the same in color. This spectra unlocks tasks like material segmentation and classification. Crucially, they can separate materials that are visually similar but physically different. In real scenes, a pixel in the captured hyperspectral scene may contain multiple materials. Spectral mixing is the process of breaking down these mixed signals into abundances and endmembers. Abundances are the fraction of the material's contribution, and endmembers are the pure spectral signatures. More specifically, each pixel is a linear combination of endmembers and abundances, where the endmember matrix must be between 0 and 1, and the abundance vector must be greater than 0 and sum to 1. Recent works has extended NeRF to the spectral modality, improving 3D spectral reconstruction. These are hyperspectral NeRF, spectral NeRF, and HyperGS. But these methods treat the spectral bands as independent channels, failing to take advantage of the rich material information encoded within the spectral signatures, and none of them allow for segmentation. So, we are the first work to include spectral unmixing modeling within the NeRF framework. This allows us to improve spatial and spectral rendering, perform unsupervised material segmentation by using the abundances vector, and performing editing using the learned endmember dictionary. This is the complete UnMix-NeRF framework. As in NeRF, we fit a 3D position and a view direction to a neural network. For each sample along a camera array, the network predicts a density and a spectral reflectance. We then integrate along the rate with volume rendering to obtain the ray spectral radiance. We divide into diffuse and specular reflectance components. Here is an illustration about diffuse and specular reflection. The diffuse component is view independent, and the specular component is view dependent. Let's focus on the view independent diffuse field. At each 3D point, we produce a density, the material abundances, and a scaling vector that absorbs illumination and environment variability. We apply a softmax to the abundances so they are non-negative and sum to 1, and a sigmoid to the scaling to keep it bounded. A global dictionary E stores the endmembers spectra, 1 per column, and the diffuse spectrum is then calculated. Now let's focus on the view-dependent specular field. From the position and the view direction, we obtain a specular reflectance. A tint factor modulates this term to control the highlight color across wavelengths while keeping it separate from the diffuse materials. We add it to the diffuse spectrum and integrate with the density using a standard volume rendering to produce the final spectral radiance. We train only with two loss functions. First, we render the hyperspectral radiance along each rate, and we match it to the measured spectrum with a mean squared error loss. Second, we project that spectrum to RGB using the camera response, and we match it to the RGB image. Now we use the unmixing components for unsupervised material segmentation. Given the learned endmember dictionary E and a rendered spectrum C of R, we compute a normalized similarity between the spectral signature and each learned endmember. Next, we apply a softmax to those normalized similarities. And finally, we pick the material with the highest probability for each ray. The good news is that with this approach, we don't need manual labels. Segmentation emerges naturally from the learned spectral structure. Next are the datasets we use it to train and test UnMix-NeRF. The first one is NESPOF, a synthetic dataset, and the second one and the third one is surface optics and bispec with real images. To enable quantitative evaluation of material segmentation, we extended the NESPOF dataset with ground truth material labels for all synthetic scenes. On the NESPOF test scenes, UnMix-NeRF delivers a state-of-the-art novel view quality, higher PCNR and equal or lower root mean square error than hyperspectral NeRF and the NESPOF method, while trained in minutes rather than hours. On the real surface optics dataset, UnMix-NeRF ranks first on both Rosemary and Basile scenes, outperforming HyperGS and achieving the lowest SAM and root mean square error, showing more faithful spectra across materials, not just sharper RGB. Similar trends are observed in the Pinecone and Anacamperos scenes, where our approach provides both higher reconstruction fidelity and better spectral consistency. Now we show for the Caladium scene frame 51. The top row is a single spectral band for each method next to the ground truth. Bottom row visualizes mean relative absolute error, where lower is better, so darker blue means less error. Our reconstruction is the cleanest, fewer artifacts and better preservation of fine-grained structure. Here we show some components of UnMix-NeRF rendered. Across the top, you see the spectral reflectance at several wavelengths. Notice how the relative response changes as the wavelength shifts. On the bottom left is the specular reflectance, and on the bottom right are the learned material abundances. On the left, here is a rendered RGB view from the hot dog scene. In the middle, you see the unsupervised material segmentation, and on the right, we do a material level edit, which changes the members in the scene, and the edit propagates coherently across the scene. This is the Ayara scene. The top row visualizes the learned material abundances. The bottom left is the rendered RGB. In the middle, there is the unsupervised material segmentation, and on the right, there is a PCR projection of the predicted spectra that acts as a sanity check and clusters the same regions. Let me leave you with three takeaways. UnMix-NeRF is the first 3D NeRF method to integrate spectral unmixing. Spectral segmentation emerges from endmember estimation, and endmember level editing enables intuitive scene control. Thank you very much for your attention. For more details, please visit our poster and read our paper.